The moon. For millennia, it has been the silent sentinel of human history, a silver disk of mystery hanging in the black velvet sky. We looked up, we dreamed, and for a brief, glorious moment, we touched it. Then, for 50 years, silence. The footprints of Apollo remained, undisturbed monuments to a bygone era of American triumph. The space race was over, or so we thought. But what if the greatest secrets of our closest celestial neighbor were only just beginning to be uncovered? What if, while the world was looking elsewhere, a new, far more ambitious lunar race was being run? Not for glory, but for survival. Imagine a world where the moon is no longer a distant dream, but a crucial, contested territory. A world where the next great technological leap, the next source of sustainable energy, and the key to humanity's future in the cosmos is buried beneath the lunar dust. This is not science fiction. This is the reality forged by a nation that waited patiently, learned from the past, and then, with breathtaking speed and precision, unveiled a series of discoveries so profound, so utterly game-changing, that they have sent a shockwave through the global scientific community and rewritten the very playbook of space exploration. We are talking about China and its astonishing, almost unbelievable findings on the moon. In the next 2 hours, we are going to take a deep, immersive journey into the heart of this new lunar frontier. We will peel back the layers of geopolitical tension, scientific breakthrough, and sheer human ambition to reveal what China has truly found and why it matters not just for them, but for every single person on Earth. This is a story of patience, power, and the profound secrets hidden in the lunar regolith. It is a story that will redefine our place in the universe. And if you are ready to have your understanding of the moon completely shattered and rebuilt, then take a moment to like this video, subscribe to CosmoDepth, and join our growing community of cosmic explorers. Your support is the fuel that keeps this journey going, and we have only just begun to scratch the surface. For decades after the final Apollo mission, the moon was dismissed as a cold, dead relic, a geological museum piece. The prevailing wisdom held that it was bone dry, resource poor, and strategically irrelevant. The focus shifted to the distant planets, to Mars, to the outer solar system. But the silence of the moon was deceptive. It was a silence filled with untold potential, a potential that China's space program, the China National Space Administration, CNSA, recognized with a clarity that few others possessed. They saw not a finish line, but a starting block. The Chinese lunar program, known as the Chang'e program, named after the mythical Chinese goddess who flew to the moon, was conceived not as a rush, but as a methodical, three-phase, three-step journey: orbiting, landing, and returning. It was a masterclass in strategic, long-term planning, a slow burn that would eventually ignite the most intense period of lunar exploration since the 1960s. The first step was Phase 1, orbiting. This was the reconnaissance phase, a necessary prelude to any physical presence. In 2007, the Chang'e 1 orbiter was launched. Its mission was simple yet crucial: to create the first complete three-dimensional map of the moon's surface. This wasn't just about pretty pictures. This was about establishing a baseline, identifying potential landing sites, and most importantly, testing the deep space communication and control technologies that were essential for the more complex missions to come. Chang'e one spent 16 months in lunar orbit, beaming back high-resolution data and laying the technological foundation for everything that followed. It was a quiet success, a declaration of intent whispered into the void. Then came Chang'e 2 in 2010. This mission was a technological leap, designed to refine the data gathered by its predecessor and, critically, to test the systems required for a soft landing. It was sent to orbit the Moon at a lower altitude, providing even higher resolution imagery of the planned landing site for the next mission, Chang'e 3. But Chang'e 2 didn't stop there. Once its primary mission was complete, it was redirected on a grand tour of the solar system. It flew past the Earth-Sun L to Lagrange point, a gravitationally stable point in space, and then, in a stunning display of deep space navigation, it performed a flyby of the asteroid 4,179 Tutatis. This was China signaling its capabilities, demonstrating that its lunar program was not a dead end, but a gateway to the wider cosmos. The message was clear. China was not just interested in the Moon, it was building the infrastructure for interstellar reach. These initial missions were the quiet opening moves in a high-stakes game. They were the proving grounds for the next, far more dramatic phase of the program, the landing. And it is here, in Phase 2, landing, that the Chinese program truly began to diverge from the historical path, setting its sights on a location that had eluded every other nation for half a century. The Moon's far side, the side that never faces Earth, the side that held the most profound secrets. The far side of the Moon is a place of stark, alien beauty, a hemisphere scarred by a much higher density of impact craters and lacking the vast, dark plains, the Maria, that characterize the near side. It is also shielded from the electromagnetic noise of Earth, making it the most radio-quiet place in the inner solar system, an ideal location for deep space astronomy. But its greatest challenge is communication. Since it never faces Earth, a direct line of sight is impossible. Any mission there requires a dedicated relay satellite, a technological hurdle that had previously been deemed too complex, too costly, and too risky. China, however, refused to back away from the challenge. They were ready, and they chose one of the most extraordinary targets imaginable, the vast von Karman crater, a 186-kilometer wide scar nestled deep inside the colossal South Pole Aitken Basin, stretching nearly 2,500 kilometers across and plunging up to 8 kilometers deep. The South Pole Aitken Basin is one of the largest, oldest, and most perfectly preserved impact features anywhere in the solar system. A titanic wound from the violent infancy of our cosmic neighborhood. Scientists believe this ancient collision was so powerful that it punched through the Moon's crust and excavated material from the long, buried mantle, flinging it across the surface like pages torn from a forbidden book. Landing here wasn't merely ambitious. It was like lowering a probe into the Moon's deepest geological archive, a frozen vault holding clues to how our nearest neighbor formed billions of years ago. That historic probe was Chang'e 4, launched in December 2018 on a journey no one had ever attempted. Yet before the lander could even fire its engines for descent, another spacecraft had to be perfectly positioned. The Xiao relay satellite, named after the mythical Magpie Bridge that unites lovers across the Milky Way in Chinese legend, Xiao was sent far beyond the Moon to the Earth-Moon. L2 Lagrange point, a quiet pocket in space where gravity from the two bodies balances just enough to keep a satellite almost motionless relative to both. From that distant perch, Xiao could constantly see the hidden far side while staying in touch with controllers on Earth, becoming the indispensable, invisible thread that would carry every command and every discovery home. On January 3rd, 2019, in a maneuver watched by millions yet carried out in utter silence, Chang'e 4 gently settled onto the floor of Von Karman crater, the first spacecraft ever to soft land on the far side of the Moon. A few hours later, a small ramp unfolded, and the six-wheeled U-22 rover rolled down onto alien soil, its golden thermal blankets glinting under an unfamiliar starfield. From that moment, humanity's eyes were finally open on a landscape no one had ever directly seen before. The revelations came quickly, and they were rarely flashy, but each one chipped away at decades of certainty about a lifeless, bone-dry moon. U-22's ground-penetrating radar pierced tens of meters beneath the surface, painting a picture of layered regolith and buried ejecta far more intricate than models had predicted. Evidence of a violent, chaotic history written in the rock itself. Scattered across the crater floor lay chunks of breccia, jagged mosaics of shattered rock fused back together by the intense heat of ancient impacts. Silent witnesses to cataclysms that reshaped the basin long before life appeared on Earth. Then, in late 2019, the rover's cameras spotted something truly strange. A dark, glossy, almost gelatinous substance pooled inside a small, fresh crater, gleaming unnaturally against the pale grey dust. Images beamed back through Xiao sparked a global frenzy. Social media lit up with talk of alien life, secret bases, or some unknowable lunar phenomenon. When the karma analysis finally arrived, the truth turned out to be even more fascinating than the wildest speculation. The mysterious gel was a type of impact-melted glass, a shiny, obsidian-like material created when a meteorite strike instantaneously liquefied the surrounding rock, only for it to cool and solidify in seconds. Far from being a one-off oddity, this glassy breccia was a vital clue, a tangible record of the moon's extreme past, and a hint that these glassy pockets might be quietly trapping something far more precious than anyone had dared to hope. Lunar glass beads themselves are scattered across the moon like tiny time capsules, forged in the white-hot fury of meteorite impacts billions of years ago. Yet this particular patch of glossy melt stood out because it spoke of a ferocious, localized blast, one powerful enough to liquefy rock in an instant and then freeze it into that strange, gel-like form. What truly electrified scientists, though, was not the glass alone, but what it is capable of imprisoning inside its microscopic structure. For decades, researchers had suspected that these beads act like natural sponges, capturing and sealing away volatile compounds, delicate molecules such as water, carbon dioxide, and other gases, delivered either by the relentless stream of particles from the sun or exhaled long ago from the moon's hidden interior. The so-called mystery gel was no longer just a curiosity. It was hard, physical proof that the lunar surface is quietly hoarding resources everyone once believed had been baked away eons ago. Yet, as remarkable as the glassy clue was, the crown jewel of Chang'e 4 lay deeper. By carefully studying the light reflected from rocks and soil through its spectrometers, U-2 detected unmistakable chemical fingerprints of minerals that simply do not belong near the surface. Olivine and low-calcium pyroxene, typically found dozens or even hundreds of kilometers down in the Moon's mantle. The colossal impact that carved the South Pole Aitken Basin billions of years earlier had apparently dug so deep that it flung pieces of the Moon's hidden heart across the crater floor. For the first time, humanity was looking directly at material from a layer we had never touched, offering an extraordinary chance to finally decode how the Moon formed, cooled, and evolved. The far side, long dismissed as inaccessible, was revealing itself as the greatest untouched library of lunar history. Chang'e 4 had delivered a technological miracle and a cascade of tantalizing hints, but it was always meant to be the opening act. With far-side landing and communication now proven, China could stride confidently into Phase 3. Sample return, the most intricate and demanding chapter of the entire program. The dream was no longer to study the Moon from afar, or even in place. It was to scoop up its most revealing secrets and carry them home for the world's laboratories to dissect under perfect conditions. That monumental task fell to Chang'e 5, launched in late 2020 on a mission of breathtaking complexity. This was not one spacecraft, but 4 working in perfect harmony. An orbiter waiting patiently overhead, a lander to touch down, an ascender to lift off again from the lunar surface, and a re-entry capsule built to survive the fiery plunge back through Earth's atmosphere. No one had attempted anything this elaborate since the Apollo era, yet the Chinese team executed every step with almost eerie precision. Their chosen hunting ground lay on the near side in a rugged volcanic region called the Marius Hills, inside the vast plain known as Oceanus Procellarum. Unlike the ancient battered highlands visited by Apollo and the old Soviet lunar missions, all more than 3 billion years old, this area is geologically youthful, with lava flows dated to roughly 1.2 to 2 billion years ago. That age gap is everything. By bringing back younger rocks, Chang'e 5 promised to fill one of the largest blank spots on the lunar timeline, helping scientists piece together when and why the Moon's internal fires finally began to fade, and what that cooling history tells us about the birth and evolution of worlds across the solar system. In November 2020, after a textbook descent through the lunar dawn, the Chang'e 5 lander settled onto the rugged volcanic plains with feather-light precision. Over the next 2 days, it worked swiftly and alone. A robotic arm scooped loose surface regolith, while a drill bored more than a meter deep, gathering fragments of ancient lava that had cooled billions of years earlier. In total, 1.73 kilograms of precious lunar material, grey powder, glassy beads, and jagged basalt chips of basalt, were sealed into a gleaming ascent capsule. Then came the moment no one had attempted in the modern era. The small ascender ignited its engine and blasted off from the Moon, climbing into orbit entirely on its own. High above the surface, it chased down the waiting orbiter, matched speeds, and performed a robotic arm guided the 2 spacecraft together in a flawless autonomous docking. The first time such a delicate ballet had ever been performed around another world. The samples were transferred, the ascender was cast away, and the orbiter fired its engines for the long journey home. On December 16, 2020, a fiery streak crossed the night sky over northern China. The re-entry capsule parachuted gently onto the frozen grasslands of Inner Mongolia, the first lunar sample return capsule to touch Earth in 44 years. When scientists in pristine white suits finally cracked open the sealed container, they found material almost untouched by any atmosphere since the rocks first solidified. An immaculate time capsule from a younger, still fiery moon. Analysis began immediately in laboratories across China, and the discoveries came thick and fast. Among the tiny grains, researchers identified an entirely new mineral, a transparent phosphate crystal they proudly named Chang'e-Y, the first lunar mineral officially recognized since the Apollo era, and a point of enormous national celebration. Yet the real earthquake was still to come. Locked inside glassy beads and crystalline structures throughout the samples were unmistakable traces of something no returned lunar rock had ever shown so clearly before. Water. Not vast oceans or hidden ice caves, but genuine H2O molecules and hydroxyl groups chemically bound into the basalt itself. And even more intriguingly, concentrated inside those impact-generated glass spheres. After decades of hints and indirect evidence, Chang'e 5 delivered the smoking gun. Physical, uncontaminated samples proving that water exists across the lunar surface in forms we can actually use. The moon was no longer the bone-dry desert of textbooks. It was a world quietly holding on to one of the most precious resources in the solar system. Detailed laboratory work on the Chang'e 5 samples soon painted a picture far more astonishing than anyone had dared predict. Tucked inside those tiny glass beads and woven into the crystal lattice of the basaltic rocks were actual molecules of water, real H2O, along with hydroxyl groups, the chemical building block of water itself. These were the very same kind of glassy spheres that had sparked the mystery gel excitement on the far side, now revealed under powerful microscopes as microscopic sealed vaults. Each bead, no bigger than a grain of sand, acted like a perfect time capsule, safeguarding water that had been trapped during violent impacts or baked into the rock when ancient lava cooled. This was not rivers or hidden lakes, nor the thick ice deposits suspected at the poles. Instead, the water existed in trace amounts, parts per million. But it was everywhere, a faint yet stubborn presence threaded through the lunar soil from equator to pole. The discovery detonated like a bombshell across the planetary science community. For generations, the moon had been declared anhydrous, completely devoid of water in any usable form. Now, hard evidence showed a dynamic, ongoing process, the solar wind, that ceaseless river of charged particles streaming from the sun, slams hydrogen ions into the surface day after day. Those ions bond with oxygen already in the regolith to form water and hydroxyl that get locked away inside fresh glass beads or adsorbed onto soil grains. Far from a one-time event billions of years ago, this is a living delivery system still operating right now, quietly sprinkling the entire moon with one of the most precious substances in the solar system. Even more tantalizing were hints from the younger volcanic rocks themselves. A small but unmistakable fraction of the trapped water carried isotopic signatures that could only have come from deep inside the moon. Primordial water carried up by magma long ago. This whispered that the lunar interior is not the bone-dry husk we once imagined, but a body that may still retain a subtle, ancient hydrological heritage. The moon, it turns out, possesses its own slow-motion water cycle, delivered from the sun, stored in glass and minerals, and occasionally released again by fresh impacts or gentle heating, crucial as water is for life and rocket fuel, it was only half of the revelation that sent shockwaves around the world. Hidden among the same samples, locked inside the newly discovered mineral Chang'e site-Y, scientists found measurable traces of an element many had spoken of almost mythically: helium-3. Helium-3 is the lighter, non-radioactive sibling of the helium we use in balloons. On Earth, it is vanishingly rare, 1 atom for every million of ordinary helium-4, because our planet's magnetic field and atmosphere deflect most of the solar wind that carries it. The Moon, naked to that wind for billions of years, has been collecting helium-3 in its soil like dust on a windowsill. Estimates suggest tens to hundreds of parts per billion are embedded across the surface, adding up to potentially millions of tons in total. Why does this matter? Because helium-3 is the ideal fuel for a neutronic nuclear fusion. When fused with deuterium, it releases its enormous energy almost entirely as charged particles rather than neutrons, meaning almost no radioactive waste and far greater efficiency than today's fusion experiments. A single shuttle load of helium-3, perhaps 25 tons, could theoretically supply all of the United States' electricity needs for an entire year. With nothing but clean power and a bit of ordinary helium as exhaust, for decades it has been the ultimate prize whispered about by space resource visionaries. A fuel that could end energy scarcity on Earth and power humanity's expansion across the cosmos. And now, returned in Chinese sample capsules, was the first undeniable proof that this dream fuel truly exists in minimal quantities beneath the lunar dust, by directly confirming measurable traces of helium. 3 embedded in the returned regolith and locked inside the crystals of the newly discovered Chang'e site-Y mineral. The Chang'e 5 mission delivered ironclad evidence that the Moon is nothing less than a vast, untapped energy reservoir on a scale almost impossible to comprehend. Conservative estimates drawn from decades of solar wind implantation models and Apollo-era data place the total lunar inventory of helium-3 somewhere between 1 and several million tons scattered through the upper layers of the regolith. Enough, when eventually fused in advanced reactors, to meet humanity's current energy needs for hundreds or even thousands of years without producing meaningful radioactive waste. What China brought home in those small sealed capsules was far more than ancient dust. It was the first tangible blueprint for an entirely new era of clean, limitless power that could one day flow from the Moon back to Earth. At its heart, the shocking discovery can be distilled into 2 simple yet revolutionary truths. The Moon is wet, and the Moon is an energy vault. It is no longer a symbolic target for flags and fleeting footprints, but a world demanding mines, refineries, and eventually power plants under the stars. This profound shift in perspective is the spark igniting a new lunar race, one infinitely more consequential and fiercely competitive than the political sprint of the 1960s. Because now the prize is not prestige, but the raw materials that could reshape civilization itself. All eyes and all future missions are now converging on the one place where these 2 treasures come together in spectacular abundance: the lunar South Pole. This is the focal italicized pivot of China's accelerating program. the target zone for Chang'e 6, 7, and 8, and the region believed to hold the richest, most accessible deposits of frozen water ice anywhere on the moon. Imagine a landscape of jagged craters near the moon's southern limb, where the sun skims forever along the horizon, casting mile-long shadows that never lift. In the deepest of those permanently shadowed craters, some plunging hundreds of meters, the temperature hovers at a merciless minus 240 degrees Celsius or lower, cold enough to trap any stray water molecule for billions of years. Over eons, comets and solar wind hydrogen have delivered trace amounts of water vapor that drift across the lunar surface until they tumble into these frigid traps, freezing solid and building up layer upon layer of nearly pure ice mixed with dark regolith. Orbiters from NASA, India, and now China have mapped these cold traps in exquisite detail, confirming billions of tons of water ice locked away, enough to supply entire fleets of spacecraft or sustain thriving human outposts. The breakthrough mission in this campaign was Chang'e 6, launched in May 2024 and already one of the greatest achievements in exploration. History building on everything learned from Chang'e 5, this far more complex probe targeted the Apollo Basin, deep inside the ancient South Pole Aitken crater system on the hidden far side. Using the upgraded Xiao 2 relay satellite for communication and an even more sophisticated lander-ascender pair, it successfully gathered nearly 2 kilograms of far-side soil and rock, the first samples ever returned from humanity's unseen hemisphere, before lifting off, docking in lunar orbit, and sending its precious cargo home in June 2024. Those samples are now revealing the far side's unique geology, including fresh clues about mantle material and the distribution of volatiles that will guide every future resource hunt. Yet the true tipping point comes next with Chang'e 7, targeted for launch around 2026 in a bold, direct assault on the South Pole itself. This is a symphony of coordinated spacecraft, a powerful orbiter for high-resolution mapping, a robust lander, a long-range rover to scout sunlit ridges, and most exciting of all, a small, agile mini-flying detector, a hopping, autonomous probe engineered to leap or fly into the pitch-black, bone-chilling depths of permanently shadowed craters where no wheeled vehicle could ever survive. Armed with spectrometers and drills, it will touch the ice directly, measuring its purity, thickness, and exact composition in real time. This mission is not merely exploration, it is the opening act of in situ resource utilization, the art and science of living off the lunar land, because lunar water ice is far more than something to drink. Split a single ton of it through electrolysis, and you get roughly 740 kilograms of breathable oxygen and 260 kilograms of hydrogen. Enough, when combined and liquefied, to fuel a rocket capable of lifting payloads many times heavier than anything we can economically launch from Earth. A refueling depot built on the South Pole would turn the moon into a cosmic gas station, slashing the cost of missions to Mars, the asteroids, or beyond by factors of 10 or more, and making routine travel across the inner solar system as practical as flying across continents today. Finally, around 2028, or shortly after, Chang'e 8 will arrive as the crucial technology demonstrator, testing the machines and processes needed to transform raw, lunar material into usable infrastructure. Robotic arms will sift regolith and feed it into solar furnaces or microwave sinterers to 3D print landing pads, habitats, and roads. Small reactors will extract and purify water ice on site, running closed-loop life support experiments that recycle air and waste. Chang'e 8 is the vital bridge, proving that permanent self-sustaining outposts are not decades away, but within reach of the next wave of missions. Together, these expeditions form an unbroken chain. Confirm the resources, map them precisely, demonstrate how to use them, and lay the foundation for the International Lunar Research Station that China and its partners plan to begin building by the early 2030s. The silent, silver moon hanging above us every night is awakening as the most valuable real estate humanity has ever known. And the race to claim its future has already begun. Every path China has blazed with the Chang'e missions leads inexorably to one grand unifying objective: the International Lunar Research Station, or ILRS. This is Beijing's direct counterpart to the American-led Artemis program, but it is built on a very different philosophy. Where the Artemis Accords gathered dozens of nations under a framework of shared principles and coordinated landings, the ILRS is a bolder, more centralized vision. A permanent, infrastructure-heavy base planted firmly on the resource-rich South Pole, planned for initial operations as early as the 2030s in collaboration with Russia, and an expanding circle of partners from Asia, Africa, Latin America, and the Middle East. More than a cluster of habitats and laboratories, the ILRS is a declaration written in steel and lunar concrete. It signals that the era of American primacy in crewed spaceflight is being challenged head-on, and that the new contest is no longer about planting a flag first. It is about who secures lasting control over the water ice and helium-3 that lie beneath the regolith. These are not abstract scientific curiosities. They are the raw, strategic materials of the coming century. The country, or coalition, that can extract, process, and export them at scale will dictate the price of rocket fuel across the solar system, the cost of clean terrestrial energy, and the pace at which humanity spreads to Mars and beyond. The true shock, then, is not any single dramatic find, but the steady accumulation of evidence, delivered mission after mission, that the moon is an economic superpower in waiting. Through the unflinching, decade-spanning discipline of the Chang'e program, China has stripped away the old myth of a barren, worthless rock and replaced it with a far more compelling reality. A world soaked in usable water and laced with the fuel of tomorrow's power plants. The technology to harvest both is no longer theoretical. It is being tested in real time. The quiet silver guardian in our sky has become the most coveted territory humanity has ever laid eyes on, and the struggle to shape its future is already well underway. For ordinary people watching from Earth, the stakes could not be higher. Master Helium. 3. Fusion and the climate crisis that has haunted us for generations could be solved almost overnight. Trillions of watts of clean electricity beamed down from lunar reactors or shipped home as fuel, with no greenhouse gases and almost no radioactive legacy. Turn lunar ice into propellant, and Mars stops being a distant dream reserved for billionaires. It becomes a practical destination for thousands, then millions. A single refueling stop on the moon slashes the cost of deep space travel so dramatically that colonizing the red planet could become cheaper than building aircraft carriers here on Earth. What China has uncovered is not just a scientific footnote. It is the opening page of a new chapter for our species. One that could lift billions out of energy poverty, end our dependence on fossil fuels, and launch us irreversibly into a multi-planetary future. The drama now unfolding at the lunar South Pole is being directed from control rooms in Beijing, not Houston or Moscow. Three great forces weave together in this story: an unrelenting scientific quest to understand our nearest neighbor, a breathtaking display of technological mastery that has turned decades of impossible into routine, and a geopolitical rivalry that will decide who writes the rules for the next age of exploration. To grasp the full weight of what has been revealed, we need to follow each of these threads deeper, beginning with the one substance that ties everything together: water. The hunt for lunar water is one of the great detective stories in modern science, a tale that begins with outright disbelief in the Apollo era, wins through decades of tantalizing hints and fierce debate, and reaches its stunning resolution in the sealed sample containers of Chang'e 5. For generations after Apollo, the Moon was officially classified as anhydrous, a world completely stripped of water in any form. When astronauts brought back hundreds of kilograms of rocks and soil, careful lab tests detected no trace of H2O or even hydroxyl. The samples had been baked by vacuum and cosmic radiation for billions of years, and the verdict seemed unanimous. The Moon was a desiccated corpse, drier than the driest desert on Earth. That conclusion became textbook truth, shaping budgets, mission plans, and dreams for decades. Yet, a handful of stubborn scientists refused to close the case entirely. Scattered anomalies in the data, slightly odd hydrogen readings, faint spectral lines, kept a flicker of doubt alive. Everything changed in the 1990s. Two American missions, Clementine and Lunar Prospector, swept over the poles and detected strong signals of excess hydrogen, locked in the regolith inside permanently shadowed craters. The implication was electrifying. Those frigid traps could be hiding frozen water ice delivered long ago by comets. Skeptics countered that the signals might simply be loose hydrogen from the solar wind, not actual water at all. The debate raged on, tantalizing but inconclusive. The argument was finally settled in the most dramatic way imaginable. In 2009, India's Chandrayaan-1 orbiter carried a NASA instrument that mapped clear absorption features of water and hydroxyl across wide swaths of the sunlit surface, proof that water molecules were forming and breaking apart daily under solar influence. Weeks later, NASA's L-Cross mission delivered the knockout blow. Engineers deliberately slammed a spent Centaur rocket stage into the floor of Cabeus crater near the South Pole at more than 9,000 kilometers per hour. A shepherding spacecraft flew through the towering plume of debris moments later and saw unmistakable signs of water, tons of it, vaporizing into space before the molecules could escape the crater's cold grip. Overnight, the question flipped from, "Is there water on the Moon?" to, "How much is there and how do we get it?" China, however, refused to settle for remote sensing or impact plumes. When Chang'e 5 returned those pristine volcanic samples in 2020, Chinese scientists opened them under ultra-clean conditions and found something no previous mission had ever delivered: actual physical pieces of the Moon that contained trapped water you could measure, weigh, and touch. two separate stories emerged from the lab. First, the tiny glass beads created by ancient meteorite impacts were revealed as remarkably efficient sponges, soaking up hydrogen from the solar wind and locking it into stable water molecules for billions of years. Crucially, the longer a patch of soil had been exposed on the surface, the more water its beads contained. Direct proof of an ongoing, planet-wide delivery service still operating today. Suddenly, water wasn't confined to shadowy polar craters. It was a resource literally covering the moon from equator to poles. The second surprise came from the basalt crystals themselves. A small but unmistakable fraction of the water carried isotopic fingerprints showing it had welled up from the lunar interior with the original lava flows. Even the moon's deep mantle, it seemed, had never been completely dry. Together, these discoveries redraw the map for future explorers. Yes, the polar ice fields remain the great frozen reservoirs, billions of tons strong and relatively easy to mine. But now, any outpost, even one parked in perpetual sunlight far from the poles, could simply scoop up ordinary regolith, heat it gently in an oven, and liberate tens to hundreds of parts per million of water for drinking, breathing, or splitting into rocket fuel. This elegantly simple process, solar wind water harvesting, turns the entire lunar surface into a distributed, inexhaustible supply network and makes long-term human presence dramatically more feasible. What began as a pure scientific mystery has quietly transformed into an engineering race. Extracting and using that water is now the central organizing principle behind China's International Lunar Research Station. Every instrument, every test planned for Chang'e 7 and Chang'e 8 is laser-focused on in-situ resource utilization, turning frozen lunar ice and baked regolith into breathable oxygen, drinkable water, and tanks of hydrogen and oxygen propellant, right there on the surface. The nation that masters these technologies first won't just visit the moon. It will own the gas station that makes the rest of the solar system affordable to reach picture. This, a vast industrial outpost perched on the sunlit rim of a towering crater at the lunar South Pole, where solar panels stretch for kilometers under the weak but unending sunlight, drinking in energy like a mechanical flower forever turned toward the horizon. Just below, in the eternal darkness of the crater floor, fleets of robotic rovers, guided by pinpoint maps from Chang'e 7's daring little hopping probe, rumble across the frost-covered regolith. They dig methodically, scooping up soil laced with billions-year-old ice, then haul their loads back up the slope to a glowing processing plant. There, sealed reactors gently heat the mixture, turning solid ice directly into vapor without ever melting it. The pure water is captured, electrolyzed into hydrogen and oxygen, and stored in gleaming tanks ready to fuel rockets bound for Mars or the asteroid belt. This is the beating heart of the International Lunar Research Station, a self-reliant factory in the sky, the cosmic launch pad that will make routine travel across the solar system as straightforward as refilling a car today. The geopolitical fallout from this vision is nothing short of seismic. On one side stands the US-led Artemis Accords, now signed by more than 40 countries, yet conspicuously missing China's name. The Accords promise peaceful, transparent exploration under the broad principles of the 1967 Outer Space Treaty. But when it comes to actually digging up and owning lunar ice or helium-3, the language remains deliberately vague. Some say toothless China and its ILRS partners have chosen a different path. pragmatic, fast-moving, and openly centered on turning resources into usable products as quickly as possible. Two incompatible philosophies are now aimed at the exact same patch of lunar real estate. What unfolds next is less a foot race than a struggle for economic mastery over the solar system's vital infrastructure. The first coalition to reliably crank out thousands of tons of propellant on the moon will hold the master key to every future mission. They will decide who can afford to fly where, who refuels at what price, and who gets stranded in Earth orbit. Water, ice, and helium. Three are not curiosities in a museum case anymore. They are the oil fields of the 21st century, and the fight to control them has already slipped the bounds of polite diplomacy into something closer to economic warfare waged under the guise of exploration. This brings us to the second great thread of the story: raw technological mastery. China's triumphs are not happy accidents or sudden bursts of luck. They are the hard-won fruits of decades of disciplined investment and a willingness to bite off the hardest problems first, while everyone else hesitated. Mission after mission, the Chang'e program has racked up world firsts that quietly rewrote what engineers believed was possible. Start with Xiao, the Magpie Bridge relay satellite parked at the Earth moon, or at E2 Point, a marvel of orbital precision that keeps a constant line of sight to both home and the hidden far side. Without it, every far side rover would be deaf and blind. With it, China turned the moon's dark hemisphere into an extension of its own backyard. Then came the flawless, autonomous rendezvous and docking high above the moon heard during Chang'e 5. A delicate, robotic ballet of chasing, matching velocity, and locking together at thousands of kilometers per hour, all without human hands on the controls. That single maneuver proved China can already do in deep space what others are still practicing in low Earth orbit. A critical stepping stone to sample returns from Mars or crewed lunar landings. Chang'e 7's mini-flying detector takes the ingenuity even further. A compact self-guided probe able to leap or hover through pitch-black, ultra-cold craters littered with unseen boulders, gently touching down to sniff out ice purity in places no wheeled rover could ever reach. And underpinning every achievement is the towering Long March 5 rocket, one of the most powerful launch vehicles on Earth, capable of hurling 25 tons straight to the moon in a single roar of flame. Where other programs remain bottlenecked by limited lift capacity, China built the heavy lift muscle needed to send entire multi-module armadas in one go, removing the biggest constraint on ambition and turning grand designs into reality faster than anyone thought possible. Taken together, these breakthroughs form an unbroken chain of capability that has placed China not just in the race, but increasingly at its front. The string of engineering triumphs delivered by the China National Space Administration stands as a direct, unmistakable challenge to the long reign of NASA and Roscosmos. For more than half a century, the world looked to Houston or Moscow whenever something truly ambitious needed to be done in space. That era is ending. Today, mission control in Beijing routinely pulls off feats: far-side landings, autonomous orbital docking, sample returns from untouched terrain that others are still planning or practicing. The new space age is no longer a solo performance. It is a fierce, multiplayer competition, and China has maneuvered itself into position as a peerless rival. executing the most intricate lunar campaigns with a calm reliability that leaves the old guard watching in quiet admiration and no small amount of concern. This brings us to the third and most explosive thread of the story: raw, geopolitical rivalry. The moon, once a stage for symbolic gestures and scientific curiosity, has been transformed by the confirmation of water ice and helium-3 into the ultimate strategic high ground of the 21st century. Two great camps now face each other across the lunar South Pole, each backed by its own coalition, each pursuing a fundamentally different vision of what the moon should become. Leading one side are the Artemis Accords, spearheaded by the United States and now signed by more than 40 nations. These accords are a set of voluntary principles: transparency, interoperability, emergency assistance, and the peaceful use of space, designed to extend the spirit of the 1967 Outer Space Treaty into the new era of lunar return. Traditional American allies, the United Kingdom, Japan, Canada, South Korea, most of Europe, and others, have lined up behind it. The operational heart of the effort is the Artemis program itself. Land American astronauts near the South Pole by the end of the decade, deploy rovers and power systems, and assemble the Lunar Gateway, a modest space station in orbit that will serve as a staging post, science lab, and refueling hub for deeper missions. Arrayed against it is the International Lunar Research Station, jointly led by China and Russia and quickly gathering partners of its own. Where Artemis spreads decision-making across dozens of flags, the ILRS is deliberately more focused and hierarchical, with Beijing and Moscow setting the timeline and technical standards. China has aggressively courted countries that feel sidelined by the Western-led effort: Pakistan, Belarus, Venezuela, South Africa, the United Arab Emirates, Azerbaijan, and more, offering them meaningful hardware contributions, training programs, and guaranteed seats at the table in exchange for political and financial support. For many developing nations, the ILRS looks like the faster, more inclusive on-ramp to serious space capability. The philosophical gulf between the two could not be wider. Artemis talks in terms of sustainable exploration, shared data, and best practices. The ILRS speaks the language of infrastructure, resource utilization, and long-term economic return. One side wants norms and handshakes, the other wants mines, factories, and a permanent industrial footprint. Cooperation between the two camps is not part of either blueprint. They were built to outpace and outlast each other. Nowhere is that tension sharper than at the lunar South Pole itself. The patches of permanently shadowed craters rich in water ice are not endless. There are only a handful of truly prime locations where near-constant sunlight on nearby ridges can power operations while ice lies just a short rover drive away. Whoever builds the first robust, continuously operating base in one of those sweet spots effectively controls access to billions of dollars worth of propellant and life support resources. Intelligence assessments already suggest that China's Chang'e 7 robotic landing and NASA's crewed Artemis 3 mission are eyeing sites separated by mere dozens of kilometers. Close enough that rovers from opposite camps could, in theory, wave at each other across the frozen wastes. The stage is set for the first real standoff on another world. The stakes ripple far beyond the moon. Every successful Chinese mission is broadcast as living proof of national resurgence. a gleaming advertisement of organizational skill and technological maturity that resonates deeply in capitals around the globe. When a developing country sees Beijing deliver far-side samples or relay satellites, while others debate budgets, the message is clear. This is the partner that gets things done. The discoveries of water and helium-3 are not just scientific papers. They are geopolitical flexes on a planetary scale, signaling that the balance of power in space, and by extension in global innovation and economic leverage, is shifting before our eyes. The quiet lunar sentinel has become the arena where the next chapter of great power competition will be written. One robotic footprint at a time, we stand on the edge of an abyss of possibility, gazing up at a familiar silver face that suddenly looks entirely new. The moon, once a dusty monument to a space race long past, has become the grand arena where humanity's next act will unfold. To understand the full weight of what China has uncovered, we must set aside the breathless headlines and descend into the exact science. The elegant, unforgiving mechanisms that have turned a supposedly dead world into a treasure chest of water and clean energy. Two elements, above all others, lie at the heart of this revolution. Water, the stuff of life and rocket fuel, and helium. 3. The whisper-quiet promise of limitless power. Begin with water, because nothing else matters without it. For half a century, the scientific textbooks were unanimous. The moon is anhydrous, bone dry, from crust to core. Apollo's rocks came back parched. Any stray molecules were waved away as earthly contamination. That certainty shaped everything. Budgets dried up, missions looked elsewhere, and the moon faded into irrelevance. Yet doubt never fully died. In 2008, India's Chandrayaan-1 orbiter, carrying NASA's moon, mineralogy mapper, swept low and caught the faint infrared wink of hydroxyl and actual water molecules bound to the sunlit soil, strongest near the poles. A year later, NASA's L-Cross mission slammed a spent rocket stage into the forever dark floor of Cabeus crater. The explosion lit up spectrometers with the unmistakable signature of water, tons of it, blasting into space. The old dogma shattered overnight. Still, those triumphs were remote glimpses. China's Chang'e 5 delivered the intimate, undeniable proof. When scientists carefully unsealed the 1.73 kilograms of young volcanic soil collected from Oceanus Procellarum, they found water in two completely different forms, each rewriting a chapter of lunar history. The first, and by far the most widespread, is water born from the sun itself. Every second, the sun hurls an invisible storm of charged particles, the solar wind, across the solar system. On Earth, our magnetic field turns most of it aside, but the naked moon takes the full blast. Hydrogen ions smash into the regolith, grab oxygen from shattered minerals, and form hydroxyl that can link up into real H2O. Chang'e 5's grains showed this process frozen in time. Water concentrated in the thin, damaged rims of soil particles, exactly where billions of years of solar wind have been hammering away. The clearest proof came from microscopic beads of glass sprayed out by ancient impacts. These tiny spheres cool so fast they trap whatever gases are around, sealing hydrogen inside like flies in amber. Heat the beads today and the water streams out, pure, ready to use. This discovery instantly turned the entire lunar surface into a distributed water mine. No longer must future settlers trek to distant polar ice fields. They can simply rake up ordinary dirt almost anywhere. bake it gently and drink, or refuel. The second form was quieter, but even more startling. Water that never came from the sun at all. Locked inside crystals of apatite in the volcanic basalt were molecules carrying the isotopic fingerprint of the deep lunar interior. When those lavas erupted almost 2 billion years ago, they carried a whisper of ancient water from the moon's mantle, water that had been there since the moon itself formed. This directly challenges the old story that the moon was born scorching and dry from a titanic collision with proto-Earth. Instead, some primordial water survived, hidden away for eons, hinting that the Earth and Moon share far more of a watery heritage than anyone believed. Together, these findings repaint the Moon as a dynamic, water-bearing world with an active solar-powered hydrological cycle running right across its surface. A revelation that makes permanent human settlement not just possible, but practical. Now shift your gaze to the second half of the bombshell. Helium-3, the fuel that could power civilizations without poisoning them. Helium-3 is the lighter, rarer sibling of ordinary helium, one neutron short. On Earth, it is almost mythical, present at 1 part per trillion because our planet's magnetic shield deflects the solar wind that carries it. The Moon has no such protection. For 4.5 billion years, it has been quietly collecting helium. 3 like dust on a shelf, embedding it into the upper fluff of regolith at concentrations 1,000,000 times higher than on Earth. Chang'e 5's samples and the tiny crystals of the newly named Chang'e site Wowie mineral within them brought home the first physical proof in human hands. The magic happens in fusion. Today's mainstream efforts chase deuterium-tritium reactions inside giants like ITER, wrestling with ferocious temperatures and showers of radioactive neutrons that chew up reactor walls. Fuse deuterium with helium-3 instead, and almost all the energy emerges as charged protons, clean, directly convertible to electricity, producing virtually no long-lived waste. A single ton of helium-3 could keep a city of 10 million lit and warm for a year. The Moon may hold 1,000,000 tons or more, energy worth quadrillions if we ever crack the reactor. That is why helium-3 has been the ultimate carrot dangling in front of space resource visionaries for decades. What China has done is perform the definitive resource audit. The Moon is not merely wet. It is an immense orbiting battery charged by the Sun for billions of years, waiting for someone bold enough to plug in. The nation that learns to mine and fuse helium-3 will command energy abundance for centuries and hold an economic lever stronger than any oil cartel in history. This is why the Chang'e roadmap reads less like pure science and more like a meticulous logistics plan for off-world industry. Every mission builds on the last, pushing toward full in-situ resource utilization, living off the lunar land itself. Chang'e 6, already triumphantly completed by mid-2024, reached farther than any before it, plucking the very first samples from the far side's Apollo Basin inside the ancient South Pole Aitken scar. Those rocks are now yielding sharper answers about mantle composition, water distribution, and helium-3 variation across the hidden hemisphere, essential data for deciding where to dig first. The spotlight now swings to Chang'e 7 in 2026, a surgical strike on the South Pole itself. An orbiter will map every shadow crater in exquisite detail while the lander and rover prowl the sunlit rims. The star of the mission is the small hopping probe, a nimble, autonomous explorer designed to bound into the pitch-black, -240-degree, permanently shadowed regions and taste the ice directly, measuring purity and depth where no wheel has ever rolled. This is prospecting, pure and simple, the creation of the first true treasure map for lunar water. Chang'e 8, planned for 2028, closes the loop as the great technology rehearsal. It will melt regolith with focused sunlight and 3D print bricks for habitats. Extract water on site and crack it into propellant, and run miniature closed-loop ecosystems that recycle every breath and drop. When Chang'e 8 succeeds, the International Lunar Research Station will no longer be a drawing on a Beijing whiteboard. It will be buildable tomorrow: water and helium. 3 are no longer theories or telescope hints. They are measured, weighed, and sitting in Chinese laboratories. The quiet moon has revealed itself as the most valuable world humanity has ever touched, and the race to claim its gifts is no longer coming. It is here. The entire Chang'e campaign unfolds like a perfectly engineered symphony. First came the watchful eyes of Chang'e 1 and 2, mapping every crater and testing the long-range links. Then the daring landings of Chang'e 3 and 4 that touched the forbidden ground, followed by the exquisite sample return pirouettes of Chang'e 5 and 6 that brought alien soil home for the first time in generations. Now the focus sharpens on Chang'e 7's intensive resource survey and Chang'e 8's full-scale industrial trials. Each step locks into the next with military-like precision, a decades-long master plan whose sole purpose is nothing less than the systematic industrialization of another world. At the end of this carefully laid path stands the International Lunar Research Station, China's concrete answer to a human future on the moon. Planned for initial deployment in the 2030s, the ILRS is conceived as a sprawling, permanent complex on the South Pole's sunlit rims, part observatory, part factory, part international city, where crews from multiple nations will live for months or years, harvesting ice, printing habitats, and preparing cargoes of fuel and helium, 3 for destinations deeper in the solar system. Yet the ILRS is far more than a scientific camp. It is a geopolitical anchor, a physical declaration that a new coalition intends to stay. Russia has committed hardware and cosmonauts. Pakistan, the United Arab Emirates, Belarus, South Africa, and a growing list of others have signed formal agreements, trading political support and funding for guaranteed roles in construction, operations, and the profits that flow from lunar resources. For many of these countries, joining the ILRS is the quickest way to leap from space bystander to space stakeholder. The discoveries of water and helium-3 have therefore cracked the heavens wide open, splitting space into 2 rival ecosystems bound by very different rules. The Artemis Accords, now embracing more than 40 nations yet still missing China and Russia, extend the 1967 Outer Space Treaty into a Western-led framework of transparency, data sharing, and safety zones around mining sites. Rules meant to prevent conflict, but criticized by some as slow and overly restrictive. The ILRS coalition, by contrast, moves faster and speaks less of norms and more of results. Its philosophy is straightforward. Resources belong to whoever can reach them, process them, and use them first. Nowhere is the fault line clearer than at the South Pole, a region no larger than a small, earthly province, yet containing the overwhelming majority of accessible ice and prime solar real estate. Artemis, 3 astronauts, and Chang'e, 7 robots, are both heading for landing zones that could be just a few dozen kilometers apart. The diplomatic scramble to define keep-out zones around active mining operations is already underway, and it may prove to be the most delicate negotiation of the century. All of this forces humanity to finally answer a question we have dodged since 1969. Who exactly owns the moon? The Outer Space Treaty is crystal clear. No nation may claim sovereignty over territory. Yet it is silent on whether the ice you dig up or the helium-3 you refine is yours to sell. The Artemis side says yes, provided you play by shared safety rules. The ILR side is already acting as though possession and use are the only law that will matter in practice. What begins on the moon will not stay there. The precedent set, whether cooperative norms versus pragmatic control, will govern how we divide Mars, mine asteroids, and build orbital power stations for centuries to come. By proving the resources are real and demonstrating the technology to harvest them, China has seized co-authorship of humanity's legal and economic framework beyond Earth. Yet perhaps the deepest transformation is philosophical and economic. The moon is no longer a poetic endpoint. It is the keystone of an entirely new cis-lunar economy that loops between Earth orbit and lunar surface in a constant flow of fuel, metals, and energy. Water ice becomes cheap propellant, slashing the price of reaching Mars from tens of billions per mission to mere billions. Helium-3 becomes the feedstock for fusion reactors that could end fossil fuels forever. Ordinary regolith becomes bricks, beams, and radiation shielding printed on demand. Even rare metals locked in lunar rocks could feed industries back home once shipping costs collapse. This is the ignition key China has handed the world. Proof that the moon can pay its own way and then some. The conversation has flipped from "should we go back?" to "how quickly can we scale mining operations?" The roadmap, the samples, the relay satellites, the heavy rockets, everything is already in place or under construction. That pale light in tonight's sky is no longer just a romantic inspiration. It is a humming factory in waiting, a service station for starships, a power plant capable of lighting every city on Earth, and, whether we like it or not, the new high ground in human affairs. The secrets China has patiently uncovered have tied the future of energy, exploration, and global power on this planet to the dust of another. The race is no longer about who gets there first. It is about who gets to decide what happens next. And that decision, for better or worse, is being made right now. To fully grasp the earthquake that China's lunar missions have triggered, we must step back and trace how humanity has seen the moon across the ages. For as long as our species has looked upward, that pale orb has been far more than a light in the darkness. It has been a mirror for our deepest hopes and fears, a blank canvas onto which every culture painted its myths and dreams. To the ancients, it was divine. Selene racing across the heavens in her silver chariot, Lunar guiding Roman knights, Chang'e floating forever on her lunar palace after stealing the elixir of immortality. It pulled the oceans, quickened lovers' hearts, and marked the rhythm of planting and harvest. Werewolves howled beneath it, sailors navigated by it, poets bled ink over its cold beauty. The moon was magic incarnate, eternal and untouchable. Then came Galileo's telescope in 1609, a simple tube of lenses that shattered the illusion forever. Instead of flawless crystal spheres, he saw a scarred, mountainous world pocked with craters and slashed by shadows. Overnight, the goddess became geography, a real place of rock and dust, close enough to reach if we ever dared. 3.5 centuries later, 1969, we dared. When Neil Armstrong's boot crunched into the Sea of Tranquility, the moon transformed again, this time into the ultimate arena of human triumph and Cold War one-upmanship. Flags were planted, golf balls were hit, rocks were bagged, and the message beamed home was unmistakable. We are a species that can leave its cradle. Yet once the political score was settled, the Apollo rocks told a sobering story. Dry as bone, geologically dead, not worth the fortune required to return. The moon was conquered, photographed, and quietly filed away as yesterday's trophy. Now, through the patient, relentless work of the Chang'e program, we are living through the third and deepest revolution in how we see our nearest neighbor. China has stripped away the romance and the politics and revealed something colder, clearer, and infinitely more powerful. The moon as balance sheet, as strategic asset, as the off-world industrial zone that could decide the fate of energy and exploration for centuries. This is no longer about planting flags or taking pretty pictures. It is about who gets to mine the ice, refine the helium-3, and control the gas station that makes the rest of the solar system affordable. The tools that made this revelation possible are masterpieces of precision. On the far side, U-22's lunar penetrating radar fired pulse after pulse into the regolith, listening to echoes that painted a picture 40 meters deep, layer upon layer of buried ejecta and ancient flows, a violent history book written in stone and dust. Those maps are already telling future builders where the ground is solid enough for habitats and where vast lava tubes might offer ready-made shelters from radiation. The rover's visible and near-infrared spectrometer bathed rocks in light and read their chemical fingerprints like a detective dusting for prints. It confirmed the glossy mystery gel was impact-melted glass, but far more importantly, it spotted olivine and pyroxene, minerals that belong dozens or hundreds of kilometers down, scattered across the floor of Von Karman crater, proof that the titanic South Pole Aitken impact excavated the moon's mantle itself and flung it across the surface for us to find. Back on Earth, the Chang'e 5 samples were interrogated with even fiercer precision. X-ray diffraction and electron microprobes revealed the delicate, hair-thin crystals of Chang'e Site Y, a brand new lunar mineral laced with traces of helium-3. Isotopic mass spectrometers measured the subtle ratios of hydrogen to deuterium in trapped water, separating ancient interior moisture from the steady drizzle delivered by the solar wind. These are not just instruments. They are the keys that unlocked a vault everyone thought was empty. This steady, almost silent march through orbiters, landers, rovers, and sample returns stands in sharp contrast to Apollo's glorious sprint. Where NASA raced the clock and then walked away, China planned for generations, quietly stacking capability upon capability until the moment was right to reveal a moon dripping with resources. That revelation now powers two rival futures converging on the South Pole. The American-led Artemis Coalition speaks of norms, transparency, and shared discovery. The Chinese-led International Lunar Research Station speaks of infrastructure, production quotas, and economic return. One side wants to explore under careful rules. The other intends to exploit under rules it helps write. The flashpoint is the peaks of eternal light, sun-drenched ridges where solar panels can run almost without pause, perched just above craters of billion-year-old ice. Claim the best ridge and you command power and water in one stroke. The race to occupy those peaks is no longer theoretical. Landing sites for Artemis 3 and Chang'e 7 already overlap on the maps. What began as poetry has become geopolitics at escape velocity. The moon is now contested territory, and the struggle over its ice and helium-3 will set the precedent for every world we ever reach. Yet zoom out far enough, and the deepest shift is philosophical. For the first time in history, we are staring at a realistic path of this fragile planet. Water to breathe and burn, energy to power entire civilizations without scorching the skies, raw materials to build cities in the void. The same discoveries that sharpened rivalry also hand humanity a way out of its earthly cage. China's patient, decades-long strategy has given us the proof, the tools, and the map. The quiet light we have watched for millennia is no longer just inspiration, it is infrastructure. The future of our species is no longer bound to the thin blue horizon of Earth alone. The era of looking up in wonder is over. The era of moving in has begun. And every night, whether we realize it or not, the moon is waiting, rich, contested, and ready to change everything. This is CosmoDepth, and we will continue to explore the deepest mysteries of the universe and the future of humanity among the stars. Thank you for joining us on this extraordinary journey. If this story has changed the way you look at the night sky, please like this video, share it with a friend, and subscribe to CosmoDepth. Your support ensures that we can continue to bring you the most in-depth, professional, and compelling scientific storytelling on the internet. We'll see you on the next cosmic journey.